Ready? So first talk of this session is on homomorphic secret sharing from polynomial modulus LWE, and Pedro Capitao will give the talk.
Thank you for the introduction. I'm happy to be here to present this work with Thomas Atema and Elisa Cole about homomorphic secret sharing. So HSS is a type of secret sharing which allows parties to locally compute functions over their shares. So in the two-party setting, you can imagine we have a secret X shared between Alice and Bob. And given some public function or program P, Alice can apply a homomorphic evaluation procedure to her share XA to obtain an output share YA. And Bob on his side can do the same thing. And in the end, there is a reconstruction procedure which obtains the output P of X of the program P evaluated at the secret. So in terms of security, we just require that each of the shares individually hides the secret X. And this reconstruction function is typically additive. So the output shares are in some group, and the reconstruction function simply adds them up together. This is quite a useful form of reconstruction because, for example, it allows you to do linear post-processing of the shares. But in our work, we are actually going to consider a more general form. So more on that later. And just to give you an idea of HSS, the simplest example we can have is for linear functions in which the secret is shared as an additive sharing, so two random shares that add up to the secret. And to evaluate some linear program P homomorphically, we simply apply P to the share, and reconstruction here is also additive. But of course, we are interested in getting HSS for a richer class of programs, which in this case is going to be the class of branching programs, which you can think of as arithmetic circuits. So we have the operations of addition and multiplication. But there is a restriction which states that a multiplication always has to involve an input value. So we are not allowed to multiply two intermediate computation values. And there is an interesting line of work on obtaining two-party homomorphic secret sharing for this class of programs from different assumptions, such as DDH, learning with errors, PKC encryption. And the starting point for our work is going to be this paper by Elette Boyle, Lisa Cole, and Peter Scholl on obtaining HSS from LWE. So I won't go into much detail about this BKS construction, but I just want to give you an idea to motivate the main problem that we are going to be focusing on. So recall that we want to implement two types of operations to have homomorphically: addition, which is going to come essentially for free by linearity, and restricted multiplication. So here we have an underlying encryption scheme based on LWE, and our input values are going to be encoded as ciphertexts, and our intermediate values are going to be additive shares. So Alice is going to have this value and Bob this one, which add up to Y times the secret key. And so when we want to homomorphically compute the multiplication of an input value X and an intermediate value Y, we just have to compute this inner product, which by the properties of the LWE-based encryption is going to give an additive sharing of this expression. But what we would like to obtain is a sharing of this expression instead. So this would be the representation of X times Y. And so the main technical question is how to go from here to there. And this step is called share conversion, and it actually shows up in some of the other works that I mentioned. For example, for DDH, it's about converting multiplicative shares into additive shares. And so let's take a closer look at this problem with some simplified notation. So suppose we have this initial equation. So Alice holds a share UA and Bob holds a share UB, which add up to this expression, Q over P times a message M plus some error or noise. And what we would like them to do is for Alice to locally convert her share UA into some value ZA and Bob to convert UB into ZB, which sum up to M. So in a way, we want to convert this additive sharing of a noisy encoding of M into a simple additive sharing of M. So this is the main technical question. And what they do in the BKS paper is split this transformation into two steps. The first is called rounding, and it's going to give us an additive sharing of M modulo P, and then a lifting step, which turns this into a sharing modulo Q. So what are these transformations? Rounding of a share U is going to scale it by multiplying it by P over Q, and then it's going to round it to the nearest integer. So here you have a visual representation of that operation. On the outside in green, you have the ring of integers modulo Q, and on the inside, the ring of integers modulo P, where in this figure, P is equal to 2. So you can see that any value in the top half of the circle is going to get mapped to 0, and any value in the bottom half will be mapped to 1. And then the lifting operation is even simpler. It basically does nothing. So if you have some value in ZP represented by an integer, you simply get the same integer as a value in ZQ. This sounds good, but do these operations actually work? Do they get this result we want? And the answer is yes, most of the time. So let's see what can go wrong. Suppose we have our initial equation here, where our error is bounded, and suppose that our message is 0. And let's say that Alice has her share UA here, and Bob has UB over there. Now, what's going to happen is that since Alice's share is in the bottom half of the circle, it will be mapped to 1, and Bob's share is in the top half, so it will be mapped to 0. So in the end, if we sum the shares after rounding, we get 1 plus 0, which is 1, and not our original message M, which was 0. And this can happen whenever one of the shares is in this red bad area. And the probability of landing there is this expression, which is proportional to P over Q. And a similar type of correctness error can happen in the lifting operation. So overall, the error probability for each multiplication operation is going to be of the order of P over Q, which comes from rounding, plus B max over P, which comes from lifting, where B max is a bound on the values that the program can take. And what do they do in the BKS paper? Well, they just say that they choose the parameters such that this probability is negligible. So that means choosing Q, which is the LWE modulus, to be super polynomially larger than the plain text modulus P, and P to be super polynomially larger than the bound B max. And in our paper, we actually show that this is the best you can do if you insist on having additive reconstruction. So now let's see what we can get if we relax this restriction. So let's consider an alternative method of rounding, in which is asymmetric. And now Alice is going to, again, scale her share by multiplying by P over Q. But instead of rounding to the nearest integer, she's always going to round down. And Bob is always going to round up. So if we go back to our previous example where Alice had her share here, now her share will be rounded down and mapped to 1, and Bob's share will be rounded up and mapped to 1 as well. So we get 1 plus 1, which is 0, as intended. So we have solved the correctness error we previously had. But of course, this method cannot be perfect. Instead of failing in the red area, it's going to fail in some other area. But observe that now we have two methods, one which works everywhere except the red area, and one which works in the red area. So let's try and combine them. And let's imagine for a second that we allowed communication, and then with just one bit of communication, we could solve this problem by having Alice tell Bob whether or not her share is in the bad area. If Alice's share is outside the bad area, then they can both use the standard rounding procedure that we saw earlier. And if it is in the bad area, they use this alternative method. So this prevents the error. But of course, in HSS, we do not allow this type of communication because homomorphic evaluation has to be local. But now suppose that we were to sort of push this communication down to the end of the protocol into the reconstruction phase. Then Alice could just round according to whether or not she is in the red area, and at the end she would tell Bob if she was or not. Well, on Bob's side, he also has to perform his homomorphic evaluation, and he doesn't know what Alice is doing. So he has to prepare for both cases, right? He has to do the standard rounding and the alternative rounding. And this is a problem because then he gets two possible values, and for the next multiplication operation, those two will turn into 4 and so on. And so Bob's computation cost is going to grow exponentially in the number of multiplications, which of course is something we do not want. But now the crucial observation is that Alice and Bob's shares are actually correlated, because we know that their sum is very close to a multiple of Q over P. So in this case, their sum has to be either close to 0 or close to Q over 2. So we can notice that if Alice's share is in this red area, then Bob's share must be in this slightly larger yellow area. Or in other words, if Bob's share is outside of the yellow area, then Alice's share must be also outside of the red area. So without communicating, they both know that they can use the standard rounding method without risk of an error. So this is what we use in our construction. So Alice is always going to check if her share is in the red area and use the appropriate rounding method. And Bob, if his share is in the yellow, is outside the yellow area, he knows he can use, he knows Alice's share is also outside, so he can just use the standard rounding. But if it is inside the yellow area, then he doesn't know what Alice is doing, so he has to compute both possible values. But we note that the probability of landing in this case where Bob has to do additional computation is given by this expression, which we can make very small while still having better parameters than the previous work. And pretty much everything that I said for the rounding operation also happens for the lifting operation. So there is a similar type of correctness error, and we can address it in a similar fashion. So I already mentioned that our reconstruction is not going to be additive. So what does it look like in the end? Well, Alice is going to have a share of this form, an integer value, and a sequence of zeros and ones denoting when she used the standard rounding and when she used the alternative rounding. And Bob is going to have a list of shares of the same type, one for each sort of computation path in the computation tree. And the reconstruction function is simply going to match the sequences of flags and sum up the corresponding integers. So as you can see, despite not being linear, this is a relatively simple function. So to summarize our results, we construct a two-party homomorphic secret sharing scheme for the class of branching programs from the LWE assumption with a small modulus, which in particular is not required to be super polynomial. We do this using a new technique for correcting or preventing errors, with which we obtain perfect correctness at the cost of variable running time, because as you recall, Bob's computation time is going to depend on how often he lands in his yellow area. We have a relaxed form of reconstruction, which makes our protocol particularly suitable for settings in which there is no security against the party doing the reconstruction. So you can think of private information retrieval and similar applications. And finally, our construction is more efficient than the previous work. We computed some concrete parameters based on ring LWE. And even for rather large programs, our shares are shorter by a factor of 4 or 5 at least. That's everything. If you're interested, please check out our paper, and thank you very much for listening.
Questions? So one thing I wanted to ask, at the beginning, you were talking about each multiplication has to be connected to an input. Was that for the previous scheme or both?
For both, yes. Our scheme is for the same class of programs.
Okay.
Yes.
And is, I guess the error just multiply, or why does connecting it to the input somehow keep the error small, even if it was growing? I guess I don't quite see how the error grows in that case.
Yeah, so it's not necessarily about the error. This allows us to, having this restriction allows us to encode the shares in this form. So we sort of have, you can see here, we have a special type of encryption where our encrypted value is X, the secret X times the secret key. So you can actually generate this ciphertext without knowledge of the secret key. This secret key is going to sort of be used up on each inner product. So that's why you always need a sort of fresh ciphertext, which comes from an input value.
I see. Thank you.
Yeah. Thank you for the question.
Other questions, anybody? Okay, if not, well, let's thank the speaker again.
Okay.
Okay, the next talk will be discretization error reduction for high precision torus fully homomorphic encryption. And Kang Hoon Lee will give the talk once his microphone is set up.
Thanks for the introduction. I'm Kang Hoon Lee from Korean University School of Cybersecurity. I'm here to present our paper, Discretization error reduction for high precision torus fully homomorphic encryption. This is a joint work with Ji-won Yoon, who is my advisor. We will start with a brief introduction about homomorphic encryption, which is an encryption scheme that allows to operate with encrypted data without decryption. So the server or the cloud gets the encryption of X with the user secret key, and they evaluate the circuit for F. So they will evaluate they will get the encryption of Fx without X revealed. Then the user will get the encryption of Fx and then decrypt with his or her secret key and retrieve the Fx. So when it comes to fully homomorphic encryption, they are capable of evaluating circuit with arbitrary depths. In order to support arbitrary depths, they usually comes with a recryption procedure called bootstrapping. These are the notations we are going to use throughout the presentation. And some important notation is the large n, which I assume to be a power of 2. And I'm going to use it as the ring dimension parameter. The next parameter is the new there, which I call it the extension parameter. I'm going to explain it later. So our work is based on the TFHE scheme, which is a FHE scheme introduced by Chilotti et al. Its security is based on the learning with errors problem and is worked with 3 different ciphertext spaces, namely the torus LWE, torus ring LWE, and the torus ring GSW. I will just exclude the term torus from now on for simplicity. The LWE ciphertext encrypts a torus element M and is actually a m+1 dimensional vector of torus elements. So the ring of WE ciphertext encrypts a torus polynomial, and apart from these 2 polynomials, the ring GSW ciphertext encrypts a integer polynomial CX. But in practice, they usually just encrypt a single integer, just like the SI, the secret key of the user. So TFHE is famous for its fast bootstrapping based on the external product. It is a simple multiplication between the ring GSW and the ring LW ciphertext. So after the external product, it returns a ring LW ciphertext encrypting the MX multiplied by the integer polynomial CX. So based on the external product, TFH bootstrapping homomorphically decrypts the LW ciphertext by calculating the controlled MUX circuit for every element in the LW ciphertext. The controlled MUX is actually a homomorphic selection algorithm to select between the rotated accumulator or the original accumulator based on the value of SI. If the SI encrypts 1, it selects the rotated accumulator, the accumulator multiplied by the x to the power AI, or if it encrypts 0, it just selects the original accumulator. After the evaluation, after the evaluation, it returns the ring of WE ciphertext encrypting the rotated MX, which is rotated by the amount of the message the LWE ciphertext holds. I'm going to introduce our major contribution of our paper, the extended bootstrapping for TFHE. So given a function f over the torus, the functional TFHE bootstrapping is actually a series of these 4 algorithms. Starting from the LW ciphertext, the torus elements of the LW ciphertext are converted into a integer space modulo 2n. During this conversion, some rounding errors are added to the ciphertext. After the conversion, the homomorphic decryption circuit, which we call the blind rotation, are evaluated, and then the LW ciphertext are extracted, and then key switched back to its original key. So the cloud will get the encryption of FM bar. So our work focuses on the mod switch and the blind rotation algorithm in order to reduce the rounding error that comes from the mod switch We first observed the change of precision in TFHE bootstrapping. After some homomorphic operations, including addition or multiplications, the ciphertext is ready to be bootstrapped, and it is first mod switched to Z modulo 2n, which incurs a severe precision loss during the conversion. So it's like looking up to the most significant log 2n bits, and this makes us to use a small message precision. A typical trace for n would be a 10 to the power of 2, which is about 1000. And in that case, we can only use the message precision as like 4 to 5 bits. So what we aim here is to reduce the precision loss that comes from the mod switch by modifying the blind rotation algorithm and the mod switch algorithm. So we can use a large message space for our ciphertext. There are some approaches that aim to reduce this error. The first approach is to reduce the Hamming weight of the secret key of the LW ciphertext. The second one is to increase the ring dimension. That is, we look up to more bits of the ciphertext. Our work aims to increase the efficiency of the second approach. So enlarging the ring dimension has its pros and cons. Some advantages will be able to use a small standard deviation for the ring of the ciphertext. And like I said, we can reduce the error from the modular switch. A severe disadvantage will be the quasi-linear growth for the polynomial multiplication. And since the TFH bootstrapping consists of tons of polynomial multiplication, it brings a severe slowdown for the TFH bootstrapping. So our first proposal is a ciphertext extension to a smaller dimension to a larger one. So our extension parameter nu comes here. So if we use nu as 0, it will be just be a simple identity mapping. But if we use nu as 1, we are sending the polynomial dimension n to dimension 2n, in which the coefficients of the odd power of x will be all 0, and the even coefficients of the even power of x will be exactly the same as the original polynomial. So with this 0 padding, we extend the ring of WE and the ring GSW ciphertext into a larger dimension, 2 to the power of nu n. So we use the notation sub x to denote that these polynomials are extended by a 0 padding. The nice thing about this 0 padding is that the external product naturally follows to the ring dimension of 2 to the power of nu times n. So we can evaluate the control MUX circuit still on this larger ring dimension while we set the parameter as n. So in this case, we can modular switch to a larger dimension 2 to the power of nu plus 1 times n, thereby gaining an additional new bits of precision during the MOS switch. However, this external product on a larger dimension needs to perform the polynomial multiplication on dimension 2 to the power of nu times n. So it is quite inefficient. So we introduce our second proposal, the parallel external product. It is based on the modular isomorphism, we call it tau, which splits the polynomial into a vector of polynomials of dimension n. So we fold the large ring LW ciphertext into a multiple ring LW ciphertext of dimension n with lengths 2 to the power of nu. Sadly, the external product does not follow naturally in this case. So we have to so the public key has to satisfy some conditions. There's condition 1 and 2. So both ring GSW ciphertext and the ring LW ciphertext has to be encrypted by the extended key. Also, the ring GSW ciphertext has to be an extension from a ring GSW ciphertext of a smaller dimension n. And this is the most important condition, that the GSW ciphertext has to encrypt only the integer, not the integer polynomial. But this condition is quite common in TFH literature because their ordinary works encrypt only zeros and 1. So we can split the external product in a larger dimension to a independent external products in smaller dimension n. Using this parallel extended product, we can build a parallel controlled MUX circuit that's shaped like this. So each row are independent to each other and can be parallel and can be computed in parallel. So one CMUX circuit evaluation on the dimension 2 to the new times n is equivalent to running 2 to the new CMOS circuits of dimension n in parallel. So in summary, we propose a extended bootstrapping in abbreviation. I call it the EBS for the TFHE. So even if we use a small n for the ring, we can always enlarge the n during the bootstrapping and gain additional new bits. The new is a non-negative integer, so you can cloud can always select how big the new is. And also we are able to keep small ring dimension n, so we do not have to implement a high precision FFT to support large dimensional polynomial multiplication. Also, our plane rotation is parallelized, so we can also always enjoy the low latency of the TFH bootstrapping as long as our computational power allows. So we provide some experimental results. We implemented our EBS on top of the TFH library, along with the 3 state-of-the-art full domain functional bootstrapping algorithms. They all uses the TFH functional bootstrapping as a sub-algorithms, and the codes are available publicly at our GitHub page in that link. And this is our experimental set. So these are the parameters we used for our paper. In this presentation, we are only going to show the results for the upper half due to the time limit. And the first 3 parameters shared exactly the same parameters, except for the ring of the ciphertext. We did this to compare whether the selecting small n along with using with our EBS is better, or just selecting a large dimension for n is better. So this is the performance of the first 3 parameter set, which is non-parallel. The y-axis represents the latency in milliseconds in a logarithmic scale of base 2. The x-axis represents the log2n plus the extension parameter new that starts from 0. As you can see, using a smaller dimension for n and using our EBS is slightly better than using the large dimension for the ring dimension. So this is the performance result for the parallelized EBS. We can also see that our EBS fully benefits from the proper parallelization. To see that the precision actually grows, we evaluated some function, simple sign function over the domain -64 to 64. So we evaluated this with the full domain functional bootstrapping algorithms, and the red line here is the maximal precision we estimated with our error estimation formula. We can observe the precision in the y-axis shows a linear growth in precision as the extension parameter new in the x-axis grows. Thank you.
Any questions? I'll just ask, can you say again for this extension parameter, how do you choose it, or how does it?
Oh, extension parameter is just a non-negative integer that you can select freely. So you have to select by estimating the error from the bootstrapping and the MOS. So using a positive integer for the extension parameter decreases the mod switch error. So you can increase it as long as the mod switch error is larger than the bootstrapping error. And you can calculate that with a error estimation.
So what are like typical values that you choose for it?
It's really different from parameter to parameter.
Mm.
Yeah, so you have to manually calculate dimensions.
So what's the range in your experiments? What, like,
Oh, we used 0 to 8 in this experiment.
oh, that's the bottom axis.
Yes, the
I see.
x-axis
So 0 to 8 with these.
Yes.
And can you talk about it asymptotically also, or is it just, is it really, it's for implementing and
Sorry?
is there a way to describe it asymptotically, how you should choose it? I mean, you're saying you compare it to the two errors, but you're saying,
Yes.
I guess not, it's complicated to calculate
Yeah.
where to put it. Yeah. Okay. Any other questions? No, thanks, speaker. The next talk is verifiable capacity bound functions, a new primitive from Kolmogorov complexity. And the talk will be given by Danilo. Oh boy, Francati.
Yeah. Thank you for the introduction. This is a joint work with Giuseppe Agnese, Long Chen, Dimitrios Papadopoulos, and Qiang Tang. So let's assume we have a machine that executes a function on some input, and we want to measure the efficiency of the function. What we usually do, we measure the efficiency according to the resource usage, like time, space, and even energy consumed by the machine. We usually want to minimize this usage, but in this talk, we're going to do the opposite. So we're going to talk about functions that waste resources to get some kind of protection. So let's have an example. Suppose we have a database in which we store the hashes of some passwords. Now, if you get hacked, you can start doing an offline brute force attack and you extract the passwords. So a way to block this attack is to use a resource demanding function, so a function that wastes resources. So now if the adversary doesn't have enough resources, you are safe. At least some of the password cannot be extracted. Now, according to the time, we can have some kind of example like time lock encryption. For space, we have memory hard and code hard function, a lot of space to be computed. And also for energy, we have an example that is bandwidth hard function. So it's a function that wastes energy while you compute a function, and we're going to see the intuition behind the construction later. So, but let's change the setting now. Suppose we are in a decentralized setting in which you have an evaluator that computes the function, and then the output is sent to the verifiers to check the validity. This could be like a proof of work, and the protocol is a blockchain protocol. So in this setting, you want to protect yourself from a malicious evaluator that, for example, tries to try different inputs until you find a particular output that gives you some kind of advantage, like predicting the next block of the blockchain. And also, on the other hand, the verifiers are the honest parties, at least the majority of them. So you can use, for example, in this setting, the resource demanding function again, but now you have a problem that the honest party is going to waste resources because you need to check the validity by running the function again. So the idea here is that sometimes we need some kind of public verifiability property that we need to verify the correctness of the output without wasting resources. So the verification must be resource free, let's say. So we have an example for time that is a verifiable delay function. For space and energy, there isn't. And what we do, we introduce the notion of verifiable capacity bound function that is mainly an energy demanding function, but it's closely related with space, as we're going to see. So the intuition is that on evaluation, we are going to consume a lot of energy, and the verification is almost energy free. And now the question is, how can we measure the energy consumed by by your machine, even if we have different kind of architecture that use different amount of energy when you do some kind of computation. So the intuition comes from the paper of boundary Hart function that show empirically that they have a bottleneck called the architecture, and the bottleneck is that when you read bits from the RAM, either because you move the bits to the cache or to the CPU to perform some kind of computation, you're going to waste 1 unit of energy, and the unit is more or less the same across all the architecture we have, including ASICs, for example. So the idea is for the function is to maximize this amount on evaluation and minimize the same amount on verification. We propose some definition to define these properties. So the first property is called minimum capacity. So even if you pre-compute the function, if I give you an input and you compute the correct output of the function, then we know that the adversary is going to read m distinct bits from the memory. And this is nice because now if your cache is of size B, you can preload at most B bits in the cache, and now you're going to read at least m minus bits from the main memory. And that's the amount of energy you're going to consume. On verification, we want soundness, so you can give a proof to check the correctness of the output. It should be hard to convince the verifier when the output is not correct. And also we want efficiency, that essentially says that the verification requires reading t bits from the memory, and this t is way smaller than m, where m is the minimum capacity of the function. So we propose a construction that we go from Kolmogorov complexity to measure the space requirement to evaluate a polynomial. And then we use this polynomial to build a function. We face some problems. I mean, the construction that we have has some kind of limitation that we're going to see later. But I mean, the intuition of the work is to lay the ground of the function and the definition. So the first part is the following. So let me introduce Kolmogorov complexity. We want to measure the description of an object. So an object is a binary string, and a description of an object is a pair. So it's an algorithm T and an input alpha. And this is a valid description if T on input alpha outputs the object. Now we can look at T like at the compression algorithm and alpha as at the compression of the object, for example. Now, if we fix T, we can define the Kolmogorov complexity as the length of the smallest string that on input, that T on input the string alpha gives you an input the object. It gives you an output the object. Now, the problem with this notion now that depends on the algorithm, but we would like to have some kind of universal estimation of the complexity, especially when we want to prove security, and we can do that by using a universal Turing machine. So we set the universal Turing machine as the Turing machine of the Kolmogorov complexity. So now the description is not a pair anymore, but it's simply the input of the universal Turing machine. So from this notion, we can define sync compressibility. So an object is incompressible if the Kolmogorov complexity of the object is greater or equal than the size of the object minus C. And the cool fact is that in any given set, arbitrary set, if you know the cardinality M, we also know the number of sync compressible objects in the set. So this is the amount that you see on the slide that depends on both the cardinality M and the factor C of the sync compressibility. Okay, so that we know this notion, let me define what's the problem we want to tackle. So polynomial evaluation, we have a polynomial of degree D. And now we have a machine that takes in input some points and gives you an output evaluation on those points. And what we want to measure is the bits that you need to read from the memory to correctly evaluate the polynomial. So intuitively, what you're going to read is an encoding of the polynomial. So what we show in the paper is that suppose you have this machine on the right that takes in input D+1 points and reads a string alpha from the memory. If the machine, and assume that the machine is giving you an output, the correct evaluations. So we can say that alpha plus the points is a description for the polynomial, because you can simply take alpha, the inputs, run the machine, takes the evaluation, and then do interpolation to reconstruct the polynomial. So this means that alpha, the size of alpha is related to the Kolmogorov complexity of the polynomial. And that's what we show. So we show that if the polynomial is incompressible, then for every tuple of D+1 points that are all different, then we know that if you correctly compute the evaluations, then the size of the string that you read from the memory is more or less greater than this value here, that is d plus 1 times lambda minus L minus C. So d plus 1 is the number of coefficients you have, lambda is the size of a coefficient. The minus L is a loss proportional to the input, because that's part of the description. And minus C is the loss of the incompressibility of the polynomial. So now how can we use this to build verifiable capacity bound functions? So these are the properties. I'm going to talk about minimum capacity mainly. And the definition that I'm going to describe here is a weaker definition than the one that we want to achieve. We're going to see the limitation later. So suppose we have an evaluator that has access to tau1, tau t strings. And each of these strings is of size m. And the correct way to interpret this string is that each tau is an information encoding to the memory that you can read, interpret, and perform a correct computation on it. So in this definition, so taus are pre-computed by looking at the function. And now you get a random point. You can read one of them. You compute the output. And now we say that the function is secure if the probability of getting the correct output is at most epsilon. And this is nice because suppose you have an upper bound on t, then the only way to compute the function is to read something that is greater than m. That's what we want to prove. So now if we fix the function equal to the polynomial, we can prove the following. So if t is equal to 1, then we can use this theorem. We can set m equal to the size of alpha of the theorem. And now we are guaranteed that when you read tau, you can answer to at most d points, because otherwise you contradict the theorem. And since the point is sample random, you have disadvantage. So it's d over the input space, the size of the input space. Now, if you have more strings, your advantage is going to be multiplied by t, simply because you can read only one of those taus. The missing part is that we need a C-incompressible polynomial, and so we know the number of C-incompressible objects in a given set. The set here is the set of polynomials, and by playing with the parameters, this is the number of C-incompressible polynomials in the given set. And by playing with the parameters, we can show that for large enough C, but not too much, we can get a C-incompressible polynomial by sampling at random from the set. And this means that the function is going to have a setup to honestly generate the polynomial honestly, because we need to have an honest sampling of the polynomial. And this is the reminiscent from the BDF also that has a trusted setup. So to wrap up, in this definition, we can prove that if you read m bits, where m is close enough to the size of the polynomial, but not exactly the same, then your advantage is going to be negligible, even if you have an exponential amount of taus that you can read, you can choose from. Now, the problem with this definition is the following. Now, I'm talking about taus, so information that you can read from the memory. But to use this definition in practice, we need to have an estimation of the memory, not the number of information encoded on the memory. So we would like to say, like, if your machine has a 1 terabyte of storage, then there is no way to read less than m bits and correctly compute the output. So we need to find a way to transform this t into a memory size. And this turns out to not be easy, simply because, for example, tau1 and tau2 may have a common pattern inside. And you could encode this information into the main memory by not repeating the red pattern. And then you leverage the random access to the memory to reconstruct tau1 and tau2 when you need it. So the question is, again, what's the relation between T and a memory that is of size n that is going to encode this information? So what we show is that, what we can show is the following. So we use a counting argument, and we count according to the number of random access you do to the memory. And we can achieve this definition, that is the final one, the one that we would like, because we have a memory of size n, with the following parameters. So we have m as before, epsilon as before, and now these parameters hold if you have a memory of exponential size, but under the constraint that you do only constant number of random access to the memory. So you jump into the memory and you read only a constant number of times. Now, if you do a non-constant number of random access, where non-constant means that depends on them, now we have a very loose bound on n, and technically we don't have a clear estimation about the security of the function when you do this kind of strategy. So the question is if you can improve the estimation of the memory bound when you do non-constant number of random access to the memory while keeping m close enough to the size of the polynomial, because we want to maximize the number of bits you're going to read. There is a barrier, and the barrier is this algorithm. So there is this algorithm that takes a polynomial and pre-compute it by building a data structure. And the data structure is of this size. So n is going to be d over 1 plus delta, where delta is a constant times lambda, more or less, at least asymptotically speaking. And so it's more than the size of the polynomial, but not too much. So it's polynomial, essentially. And then on evaluation, we can evaluate the polynomial by using a non-constant number of random access and reading this amount of bits. So it's polylog d times lambda. That is way smaller than the size of the polynomial because it's polylog in the degree. So asymptotically speaking, what I'm saying is that we cannot go over these parameters, but maybe concretely by playing with the constant, we can get some kind of concrete estimation. Very briefly regarding soundness, what we show is that we have soundness by using verifiable computation that is publicly verifiable and publicly detectable. So on setup, we also generate some keys. The key allows the evaluator to produce the proof, and the verifier can use the same keys that are public to verify the proof. And regarding efficiency, what we show is the following. So we know that on evaluation, we read m bits close to the size of the polynomial, at least when we do constant number of random access. And on verification, we can show that if you use this verifiable computation here from SHCS 2016, what you're going to read from a memory is something that is proportional only to the security parameter, so independent from D. And that's why we get the asymmetry. Okay, that's the end of my talk. Thank you.
Questions? We have probably 5 minutes here, so we can, if you don't have a question, I'm going to ask a question. It's maybe a little more basic. So I'm not so familiar with this. I was wondering if you could just say again, like, what the different parties do. There's this capital F that you're working to make it hard to evaluate, right? Is that against the...
So we want to build this function that when you evaluate it, we have a lower bound on the number of energy, electricity you're going to use.
Do you have a picture with that describes the general, like just the basic setup with capital F? I think you had one.
You mean this one?
Yeah. So like, what's the difference between the left bottom picture and the right bottom picture? Like, how can somebody do verification versus that's a separate protocol, or how?
No, it's the same protocol. So that when you evaluate the function, you evaluate the function on X and you produce Y.
Mm-hmm.
But together with Y, you also produce a proof, and the proof is going to allow you on verification to check if the output is correct or not.
Okay.
It's similar to VDF, the syntax.
So then on the left, this is
on the left is the
finding a proof. Like what's the I still don't quite see the difference.
So the one on the left,
yeah,
is minimum capacity. That is the security against an evaluator. So here we're gonna say that when you evaluate the function, if the output of the function is correct, then you're gonna read m distinct bits. Now the syntax of the function also appends a proof, and then the proof is used on verification only. So on the right part now we're talking about the verifier, and we have soundness and efficiency.
So that part's easier. It's so that with the proof, it's much easier than.
Yeah, the soundness part is easier. The problem is the minimum capacity and how you estimate the memory. Yeah.
Okay. And then how does someone use it initially if it's hard to compute? Or
I mean, it's something that you can compute.
Yeah.
The problem is that you're gonna use resources. That's the.
I see. And then what's code hard? I saw that as one of the
code hard. It's like I think the clear example of code hard. It's like a function which on setup. I mean, I have an example. So on setup, you you build like a random table, and I give you the random table, and then I'm gonna ask you, give me this entry of this table. And since I'm gonna select the entry of the table at random, you need to store, let's say, the entire, the majority of the database, because otherwise I'm gonna hit one that you don't know. So that's called Dart.
Okay. Thank you. Any other questions?
So I think you mentioned the evaluation function is a polynomial, and that with high probability it is actually energy demanding. So is this a random polynomial, or is it chosen?
It's a random polynomial. I mean, it's a random polynomial for simplicity, but technically, if you have a set of polynomials of where the cardinality of this set is large enough, it's sufficient to sample from that set, at least theoretically speaking.
And the degree of the polynomial was this D that was
D.
defined.
So that you need to set D according to how much bits you want to read, because that's the only parameter for which you can play with. So the higher the D, the more the degree, the higher the majority, you have more coefficients, and that's you're gonna read more coefficients.
Okay. Thank you.
Any other questions? No? Thanks, speaker again. So the last talk of the session is a holistic approach towards side channel secure fixed weight polynomial sampling. And Marcus House will give the talk.
Okay. So hi and welcome to my talk about side channel secure fixed weight polynomial sampling. So what is fixed weight polynomial sampling? It's quite a simple problem actually. We want to generate a random bit string of length n and Hamming weight w. And for example, with n equal to 10 and w equal to 4, we have a bit string of length 10 where we have 4 ones and 6 zeros. And this bit string represents a bit polynomial with 10 coefficients. And we call this representation the coefficient representation, but we could also represent our bit polynomial in the index representation, where we simply store the indices where the bit is 1. And with this index representation, we can also rephrase our problem. So what we want is to draw W random elements from the set 0 to n minus 1 without replacement, regardless of the order. So why do we need this? Actually, we need it quite often in post-quantum cryptography. So there are some relevant schemes that use this with some variety, and the most important parameters are, of course, n and w, and the resulting ratio of w compared to n. So for Bike and HQC, for example, we have big N and smaller w, resulting in a very small ratio. For Michaelis, we have a medium-sized N, and for N-true and streamline N-true prime, the N is small and W is greater, resulting in a ratio that is close to 50%. So now you might be wondering, why are we talking about such a simple problem? So it turns out, if you want an efficient and side channel secure implementation, it's not that easy. Yeah? So side channel security, when we talk about side channel security, we first have to evaluate which values are secret and sensitive. So which values do we need to protect against the side channels? And for the fixed weight polynomial sampling, we have as inputs some randomness, and the output is a polynomial. And for other schemes, this polynomial is a secret value. So our sampler must not leak any information about the polynomial. But for some of the schemes, we have an additional requirement. So the randomness is generated by an PRNG, and the seed, the input seed, is a secret value. Therefore, the randomness is also secret dependent, and therefore our sampler must not reveal anything about the randomness. So when I talk about side channel security, talk about timing side channels, and for this our common countermeasure is constant time programming. But in this work, we also focus on power side channels, and our countermeasure here is masking. So a quick reminder about constant time programming. We basically have three simple rules there. Branches, memory accesses, and instructions with operand-dependent runtime must not depend on any secret values. And for the fixed-rate polynomial sampling, the memory accesses can be quite a problem. So for the power side channels, as Chris Peikert yesterday already introduced, we can use masking. And the idea is here, secret values are split into random shares. And for first order Boolean masking, for example, we would end up two shares that we can combine with an XOR to get the original value. And as Chris explained, the challenge here is when we have nonlinear functions, and they can be quite expensive. So what are the methods that we can use for fixed rate polynomial sampling? So there are basically 6 different methods, and we can put them into 3 distinct categories. The first category is rejection sampling. It outputs a polynomial in the index representation. And the next category is what I call setting bits randomly. It works on the coefficient representation. And the last category is shuffling. It can either work on index or on the coefficient representation. And they all also differ by what I call the seed security. So what I mentioned, whether it's possible to implement them in a way that the seed is not leaked via a side channel. So let's jump into these categories. So rejection sampling is probably the most straightforward solution for this problem. The idea here is that we sample uniform random values from 0 to n and reject a value if we have a collision. So if we already sampled the value before, and we just repeat this until we have W distinct values. Obviously, this is not seed secure, so this would leak the seed or the randomness that we are using because it determines how many iterations we have to do. But we can transform this method to make it seed secure. And we call this a bounded method. So what we do here is we determine an upper bound B of iterations in which with very high probability enough distinct values will be sampled. And then we do exactly always these B iterations. And for each value, we always iterate our whole index array to keep the current count secret. And of course, this adds some overhead. So this method only makes sense in a scenario where we require this seed security. So the next method, setting random bits. There's this repeated ending method. The idea is here that we start with a random polynomial of length n, and then we adapt the weight by ending or ORing random polynomials until our desired weight W is reached. So basically, we make use of the observation that when we end 2 random bit strings, the weight can only decrease, not increase. And if we OR 2 bit strings, it can increase but not decrease. So then we make, let's say, a clever combination of this ending and ORing to get to our desired weight. And an important observation is here that the runtime here is again dependent on the randomness we get, and also if our ratio of W compared to N is close to 50%, this method can be fast because this is like the expected weight we get from a random bit string. But if our ratio is far away from the 50%, then this method can be costly. But we have a solution for this. Yeah, for situations where our ratio is far away from the 50%, we basically have a generalization of this idea. We call it the comparison method. Therefore, each coefficient we set a bit with probability p is equal to W over n, and then basically resample the polynomial until we get one with a desired weight. And we approximate p with a comparison of a random L bit string. So basically, our p is in a range from 0 to 1, and we scale it up with 2 to the power of L. And then if we take an L bit string, it will be in this range, and we compare it with the threshold. And if it's below the threshold, we set the coefficient to 1. If it's above, we set it to 0. And in a masked setting, we can do this bit slice, so it's also parallelizable, so very comparable to the ending method, actually. Last methods are the shuffling methods. The idea is here that we start with a fixed polynomial of length n and a correct weight W. and then just apply a random permutation. Yeah, so for example, we set the first W coefficients to 1 and do a random shuffling, and then we end up with a random polynomial. Question is now, how do we do the shuffling? One solution is to do it with sorting. So a well-known method is to pair each coefficient with a distinct random number, and then we sort the pairs according to the random number, and then we get the random permutation of the coefficients. And sorting can be somewhat efficiently be done side-channel secure. And now you might be wondering, why don't we use Fisher-Yates shuffling? Well, we can use Fisher-Yates, but it's usually not side-channel secure. It's leaking the permutation via the memory accesses, but we can transform it to make it side-channel secure, but then it becomes quadratic. But there's still a use case for this. The idea is now that we start with an array of the values from 0 to n-1. Then we apply a random permutation with Fisher-Yates. And then we take the first W entries as a polynomial in the index representation. And Fisher-Yates can be stopped after the first W entries are set. So our runtime is quadratic in W and not N. Yeah, so these are all the methods that at least we know. And we implemented them all arbitrary order masked and bit sliced in C and evaluated on a Cortex M4 microprocessor. So these are the results for the first order masking. And let's look at the sorting approach in the middle. For Bike and HQC, we actually weren't able to run it on the microprocessor because it requires too much randomness. And for McAleese, for example, with a medium-sized N, we can see it's not very competitive, the approach, yeah, because the runtime really depends on N. And for N-true and streamline N2 prime, it's somewhat acceptable. Then for Fisher-Yates, we can see, for example, for HQC and McAleese, the runtime is very competitive because it depends on W, yeah. And then the rejection method, this is not seed secure, so we cannot use it for Bike and HQC, but for the other cases, it's one of the fastest methods. And for Bike and HQC, we can use the bounded rejection methods, but this method doesn't make sense for the other ones because it's always slower than the simple rejection method. But what we can also see is that the bounded rejection method is always slower than Fisher-Yates. So actually there is no use case for the bounded rejection method. And then we have the ending and comparison methods. They are also not seed secure, so not usable for Bike and HQC. And they can be the fastest methods. And what we can also see is the comparison method is especially faster in the case where we have a ratio for McAleese, for example, where the ratio is 2%, so very far away from the 50%. So the outcome basically of our work is, yes, we have solutions, yeah, side-channel secure solutions for all the use case, but actually they are all very slow, yeah. So these numbers that you see here, they are kilocycles. So we're talking about at least 1 million cycles for such a simple operation. This is way more than we anticipated and way more that we would like to have. So we are actually still looking for a viable solution. And if you have any ideas, let me know. Thank you.
Thank you. Questions? Where I am. Well, let's thank the speaker.
Just a reminder, buses 5:30 and 6 o'clock. Hope to see you at the aquarium. Yes. Shuttle's back. The second one back at 10. I'm not sure what the first departure time will be. And we'll be meeting just the nice like drop off area right outside the hotel lobby.